Welcome back. In this video, I'm going to walk you through a few extra practice problems dealing with gases. Specifically, we're going to use the ideal gas law, look at partial pressures, and as well look at deviations from ideal gas behavior. For this first question, pause the video, try this on your own, and then come back and I will walk you through the process. Welcome back. So we have an ideal gas inside of a piston, and we're compressing the volume to half. That causes the pressure to go up from 2.3 atmospheres to 3.6. We would expect it to double. However, as the gas was compressed, some of the gas leaked out. So given that the temperature is constant, what percentage of gas molecules leaked out from the piston? So again, we would expect the volume to double if we halved the volume. So let's think about this by taking a look at the ideal gas law. We can rearrange the ideal gas law to equate it to the gas constant. And the reason why this is useful is because then we can set up a set of initial conditions and a set of final conditions. And we can relate the initial and the final conditions to each other through the ideal gas constant. We know that there's a relationship between moles, and we know that the moles are related to the pressures, volumes, and temperatures. Again, we're looking for the percentage of gas molecules that leaked out. So by taking the ratio of the moles, we can find out the ratio of how much there was to how much there was left over. We know that the temperatures are the same. Therefore, we can relate moles just to the pressures and the volume. We know that the volume, after they leaked out, was half as much as the original volume. And we know, therefore, we can cancel out the actual volume. And we know the pressures. By plugging this in, we see that the ratio of the final number of moles to the original is 0.7826. What that means then is in order to find out the actual, that's the ratio of how much is left over. So we have 78.26% left over. Therefore, to find out the amount that was lost, we take the difference between the two. And that's approximately 22%. Let's do a second question here. Pause the video and try this one on your own. Welcome back. So if we want to determine the root mean square speed of helium, what do we need? We need to use this equation describing the root mean square speed and relating it to the temperature and molar mass of the sample. Because we only need the temperature and the molar mass, and we're given the mass, we're going to need to use the other information in order to find the actual temperature. So we can use the ideal gas law in order to find the temperature by using the pressure and the volume. Now, the R value for the root mean square speed is 8.314 joules per mole per degree Kelvin. But we don't know the temperature. Molar mass is 4 grams per mole, and we need this to be into kilograms because of the units of joules. Again, we can use the ideal gas law in order to find the temperature because we know the pressure and we know the volume. So we can rearrange this equation to solve for temperature. Our moles is going to be equal to the mass of sample divided by the molar mass. The volume we need to find by converting milliliters to liters. And then the temperature we calculate. So we know that the pressure is 130 atmospheres. The volume is 0.25 liters. In this case, we've got 1¼ moles, and the R value here is a different value than the R value for root mean square speed. It's the same ideal gas constant. However, because the units are different, the number is also different. So notice here, when using volumes and atmosphere and pressures, we're going to use liters atmospheres. Whereas for the speed, we're using joules. And so that provides us with a different value. We can solve for the temperature and then plug that in to the other equation to solve for the root mean square speed. Take the square root of 3 times R times the temperature in Kelvin over the molar mass in kilograms per mole. Remember that a joule is a kilogram meter squared per second squared. That's why we need our molar mass to be in kilograms per mole. The kilograms cancel, the moles cancel, and the kelvins cancel. Then when we take the square root, we're left with meters per second, and that's about 1,400 meters per second. Here's another question. Pause the video and try this one on your own. Welcome back. So we have 3 liters of helium at 5 atmospheres, and we're mixing that together with 4.5 liters of neon at 2 atmospheres. The temperature is constant at 25 degrees Celsius, and we've mixed them together into a 10-liter vessel. And we want to know what's the pressure inside the 10-liter vessel. So you might be tempted to just add together the initial pressures. Remember, Dalton's law of partial pressure says that the sum of the pressures, or the total pressure, is just the sum of the individual partial pressures. However, take a look at the volumes. We have 3 liters of helium and 4.5 liters of neon. Together, they don't add up to be 10 liters. So what we can imagine happening is that you put them in the vessel and then they expand in order to fill that 10 liters. Therefore, we would expect a total pressure to be a little bit less than the sum of their partial pressures. So keep that in mind as we are solving this. So by using this relationship, this is Boyle's law, but this comes from the ideal gas law as well. We can relate the pressure and volume of one of the gases under the first conditions to the second condition, meaning the volume of 10 liters. So for helium, we know that its initial conditions are 5 atmospheres and 3 liters. And we're putting it into a 10-liter container. We can solve then for the new partial pressure of helium once it's in that container. And that's 1.5 atmospheres. For neon, we can solve for its new pressure in the new container. And that's 0.9 atmospheres. Therefore, according to Dalton's law of partial pressures, the total pressure is going to be the sum of the partial pressures. So we simply add them together, and we have 2.4 atmospheres. As we expected, this is lower than the sum of their individual partial pressures. In the original containers, that is. Here is another problem. Pause the video and try this one on your own. Welcome back. So in this question, we have a balloon filled with helium to a volume of 2 liters and 1 atmosphere at 25 degrees Celsius. We want to know what would the new volume be if we put the balloon in the freezer to negative 10 degrees Celsius, assuming that the pressure does not change when we put it inside. So for this problem, we can use the ideal gas law. Because we're talking about a set of 2 different conditions, a condition with it at high temperature and then at low temperature, we want to relate the initial conditions to the final conditions. So we can do that by solving the ideal gas law for R, because it's a constant, and then set that equal to the new conditions. Then, since we know that the number of moles are constant and the pressures are constant, we can eliminate them from our relationship, and we get that V1 over T1 equals V2 over T2. We can then solve for the second volume and plug in our values. Now, be very careful. It might be tempting to just put in your temperatures. However, you need to convert them to Kelvin. If you were to have just plugged in the temperatures, what you would see is that you have a negative volume, which is not possible. So always make sure that you're converting your temperature to Kelvin when using the ideal gas law. When we solve for this, we see that the volume is about 1.8 liters. So as we would expect, the volume did go down because we decreased the temperature, and therefore we decreased the collisions, and that shrunk our container. Here's one more problem. Pause the video and try this one on your own. Welcome back. So if we're given an atmospheric pressure of 755 torr, what's the total partial pressure of all the gases other than nitrogen and oxygen? Well, using Dalton's law of partial pressure, we know that the total pressure is the sum of each individual pressure. So we can substitute in for each of these different gases. Let's say, since we're looking for the total partial pressure of all of the other gases, we can clump them together. And so to solve for the partial pressure of those gases, we would rearrange and subtract the partial pressure of nitrogen and oxygen from the total pressure. In order to find the partial pressure of nitrogen and oxygen, we can use the mole fraction. So for nitrogen, we multiply the mole fraction of nitrogen times the total pressure, which is 0.78084 times 755 torr. We would repeat this process for oxygen. Then we take and we subtract those pressures from the total pressure. And that leaves us then with the total partial pressure that's contributed by the other gases. All right, here's the last question of this video. So for which of the following would we expect the gas to deviate most from ideal gas behavior? Pause the video and try this on your own. Welcome back. So what causes gases to deviate? Well, we know that for this, the deviations occur most strongly when we're at low temperatures and high pressures. But under any given set of conditions, we can compare between different gases based upon the strength of their intermolecular forces and their size, which we can relate either to the actual size of the molecule, but also the molar mass. So water is polar, but methane and neon are both nonpolar. They all have similar molar masses, so we're not going to be able to make a huge distinction between them. But if we had to determine which one deviated the most or the least, then this should be sufficient to make a distinction, especially because methane and neon both are nonpolar and both are roughly the same size. So we would expect to have to distinguish between them using their molar masses. Therefore, since water is polar and has roughly the similar molar mass, it's going to deviate most strongly from ideal gas behavior. Whereas methane is nonpolar and has a smaller molar mass, so it would deviate the least. That's it for this video. Thanks for watching.